Thank you very much, Bertrand. So I hope you hear me well. So I'm going to present you in brief the motivation and ambition of the third work package on proxy detection and Earth observation services. So my name is Xavier Draye, and I'm talking on behalf of two remote sensing experts, Pierre de Fourny in Louvain, Marie Weiss in Draye. Tom Kenda is our first PhD candidate in this work package. Arnaud and Anne are representatives of the Geosys company, who is within the time frame of this project launching a new constellation of satellites for agricultural services. So I will start with a first point is that our current phenotyping activities are usually done in a context which is related to the kind of questions that we are addressed. So in control condition, we are talking about plant physiology, genetics also obviously, but at the field level, we are more talking about crop physiology issues and modeling. Something which is still missing in terms of phenotyping for agricultural application is extending to the farming system. Going across those different dimensions raises scaling issues. First scaling issue related to the context. The more distance we are taking from the plants, the more likely we are to be facing genotype by environment issues, which are not issues because they are essentially the topic and the motivation for doing this phenotyping. A second scaling issue is the logistic. It's not the same thing to conduct trial at the across farm or regional level than to do something in control conditions. And the third one, a third scaling issue is related to the culture, in the sense that the discipline, the methods that are used across those scales are usually not the same. And this does not favor easy communication and collaboration across those scales. A second point that I want to start with is the array of technologies that do exist to provide measurements, essentially non-contact measurements, so based on radiation measurement, from the fields to the landscape level. Some of them are highly used, such as gantry systems, drones, and phenomobiles. Some are in development, like the sensors at the scale level or satellites. Well, they are not in development. Their usage in phenotyping is still limited, which is why I wanted to say. And so in the context of PHENET, we are going to use the sensor networks, the drones, and spectral imaging essentially as a model to develop tools going across those scales, assuming that the development will be also useful for the other instruments. But by doing so, we are going across the whole range of scales. Maybe the ambition that we have by developing those lines is to wider the current scope of phenotyping, which is in this gray box, taking measurements essentially with drones or phenomobile in the field, and to leverage on Earth observation and sensor network, in the sense that those technologies are either readily available, like satellites, which circulate around the Earth, then the pipelines to collect, store, analyze, and provide products that have agricultural value do exist and are free of charge for the users. And combining those satellites with networks of instruments that stay in the field in a fixed position should be a very nice complement to strengthen what the possibilities of phenotyping for service in agriculture. Opportunities that we foresee with this combination is based on the complementarity between the three selected instrument. At the remote sensing satellite level, have provide a very nice spatial coverage. Essentially, the whole planet is covered. With the rather low spatial resolution, we are speaking a few meters or more than a few. A very nice temporal coverage. The Sentinel-2 constellation from the EU is warranted to be operational for the next 20 years, since 2017. The temporal resolution is rather nice. It's less than a week, although it is facing the issue that cloud can make some acquisition not available, depending on the type of instrument. The dimensionality is, we would say, in the range of the 3 is minimum, in the sense they are measuring a number of the reflectance in a number of wavelengths, and this is all what they are going to measure. User cost is minimum, in the sense that all the service of providing this information is taken in charge by agencies at the EU level, and images are freely available. The drone and the phenomobiles have a rather low spatial coverage. They will be deployed in the field of interest and only there. They have the highest spatial resolution, probably. The temporal coverage is going to be limited to the duration of a trial, and the resolution is rather low. So in the best case, we use those equipment once a week during the season. The dimensionality is the highest because they can be equipped with whatever kind of sensor we would like to have, but the cost goes obviously with that. Then the sensor network have the lowest spatial coverage. They only see a few meters around the location of the sensor. They can have a rather high spatial resolution depending on the kind of instrument. The temporal coverage is, well, as long as the sensor is there, it is taking data, and it can take measurement at the second or millisecond resolution, temporal resolution, if that would make sense. The dimensionality will depend essentially on the cost that we agree to put on those sensors, and the cost can be dramatically reduced depending on the technology that is used. So why the combination of 3 seems to us to be rather powerful? The first is that the combination is likely to provide us with time series of data that are crucial for a mechanistic understanding of the development of a phenotype during a season. They allow us to go into the field, and also from the platform, and to go into the field. And ultimately, this is where we are aiming to go. When we talk field, we can also talk farmer field at a regional level, which is going to allow us to broaden the environment by management domain in our experiments. They can also be used for indirectly for other purpose, like some consideration related to the design of an experiment. So selecting fields when we are building trial networks can be aided if we have information about surrounding fields or past observation about those fields. And also some consideration regarding the analysis of the data, as they can be used for spatial analysis of field data. And these are the opportunities. Now, these come obviously with a number of bottlenecks. Some of them are the one we are going to tackle within PHENET. Technical bottlenecks, so the data fusion across different scales and resolution, from satellites that are at a 10-meter resolution down to phenomobiles that will be a 1-millimeter resolution. How do we merge data sets from these different instruments? From remote sensing to plant traits, so this is going to cross the different dimensionalities of those sensors. And also the validation needs of novel spectral bands. This is related to the new constellation that I was mentioning, and that will have to be validated. It's also the same for the sensors in the field that come with a different set of spectral bands. Next to those technical difficulties or bottlenecks, we have also operational bottlenecks that are more related to the research infrastructure side. Is a lack of awareness of several of our users. is a negative appreciation of data that have a low spatial resolution, is a lack of analytical expertise in terms of geographic information system database, data fusion, data mixing, a lack of training opportunities, lack of available software to allow users to collect satellite data, and lack of solutions to handle those data in phenotyping information systems. So this was an introduction, going then to the mission of our work package within PHENET, is to develop a user-ready solution, and this is highlighted because this is really what we want to achieve for a better representation of the variability in field condition, both the spatial variability and the temporal variability. The second aims is to provide a wider access, and again, this is strengthened to phenotypic data by including also multi-scale Earth observation services. And to support those aims, we set up ourselves 3 objectives. One is to account for the variability of environmental conditions in field plots, thanks to Earth observation dataset, and this is what I'm going to illustrate today. The second is to develop methods for cross-scale data fusion from Earth observation UAVs and on-field sensors, including forthcoming constellations. And the third objective is to develop and distribute plant trait estimation algorithms that are based on Earth observation services. Now, the first example, which is going to be a first result we achieved during the last 12 months in the framework of PHENET, and this is the work of Tom Kenda, who is on the picture and is also participating to the conference. Hello, Tom. Is based on the use of Sentinel-2, which is a constellation of satellites with a 10-meter spatial resolution, a revisit time which is approximately 5 days, every 5 days, and a lifetime warranty of 20 years warranted by the EU, and the data are made available through the EU Copernicus program. So one of the products that are available from this Copernicus program is an estimation of green area index, which is computed automatically every time a new acquisition is made. This product is available from the website and will provide, as illustrated here for 5 plots, an estimation of the green area index with a 10-meter resolution in the field. So this information is used in Wallonia by the Belcam platform to provide time courses over the season, so farmers can select a field, go back in the past, see what has been the evolution of the green area index over the season for their particular field. And we see here in the plain lines 2 different fields. And the system is also taking advantage of the global coverage of the satellite to provide an average of the GAI of all the fields with the same crop within, let's say, 10 kilometers. This allows to contextualize the behavior of a particular field in its region, in its pedological and weather context. So how are we going to assess the variability of the field using this GAI information? What we do is actually for a farm and for a given year to take the time course of the green area index and to take that time course for every individual pixel. So this gives us this kind of data set. We are filtering from the start of the vegetation to the end of the crop. These dates are automatically computed from the whole time series. And so here you see a set of all those green points that represent the value of individual pixels. So from that, we have developed a simple metric that will rank every pixel and localize it related to pixels that would be on average the value of that would follow on average the value of the average of the field. The pixels that are more in green would be pixels which on average during the season would tend to be higher, so with a higher green area index than the rest of the field, and the one going to the red are those that will on average during the season tend to be below the average. So we are using a relative or absolute depends. We have some discussion with the people to know exactly how we should name that scale, but essentially the scale is absolutely the same for all. So we are going from -3 times the mean to +3 times the mean, which will allow us to compare different fields, but this is related to the average of the parcel. The way we can use this information to compare different fields, and so to make a sort of absolute comparison, is to take for, let's say we have here 2 winter wheat fields within the same year in the region, take the variance or the standard deviation of this metric that we have, and we see this rather homogeneous field with a metric of the variance of a matrix being 0.05. We have here on the right a more heterogeneous field for which the standard deviation of the metric is 0.2. And we can take a regional context in the sense of a reference population of plots. And typically this would be all the winter wheat plots in the same year at a certain distance around the field of interest. So we have then the distribution of those hundreds of fields, and we can then localize the standard deviation and say, for example, that this one is a field that is within the 6% most homogeneous within the population, so related to the reference population, while this field would be at the percentile 91. And this way we have a very nice quantitative measurements that brings us the possibility to make a difference based on a reference population. So the concrete output, you remember that we say we really want to provide user-friendly solutions and readily and user available. So the concrete output is typically a sheet in which we take the complete time series for a field of interest, and there will be one sheet per field, showing the metric as a map since 2017 until today. Well, in this case, until last year, and also plotting information relative to that year, in the sense what is the crop that was grown on that plot. And the information is derived from the land parcel information system of the Common Agricultural Policy of Europe. We also provide information in terms of the climate. So what it's a hot or wet or dry year compared to the population of weather during the last century for this region. We also provide the altitude map and the, if available, the soil map information, plus a picture of the field from Google. We have discussed with farmers to have a first validation of the tool, farmers being the one who are the best positioned to assess and to contextualize the heterogeneity of their own fields. And so here we have a field where the heterogeneity across 2 different years is nicely consistent with the soil map and also the elevation. And this was confirmed by the farmers with areas of the soil that are more sandy and therefore show a higher dependence to or sensitivity to water deficit. We also detected that field that was well, strikingly split it in 2. It was actually the same crop, but the farmer told us it was 2 different plant index that he applied. Then we have also a situation where these bands were actually revealed to be a poor dissolution of the product in the sprayer, and the farmer could remember that also a situation where you had to change the fertilization level by changing the machine during the fertilization of a plot, and this was actually visible. So this shows that the tool is actually revealing things that make perfect sense to the farmer and to the agricultural management of the plot. This is another illustration of the tool, showing that it is also sensitive to scientific activities that we are doing on some plots. And here we have another trial. And in 2023, a wheat trial was done with 4 different treatments, and we can clearly see those 4 treatments. Now it is interesting to see what was the behavior in the past, and probably information coming from the rapeseed 2 years before is a little bit interesting and suggests that it's not always visible depending on year and crop, but there was potentially a zone of heterogeneity in this part of the field. Another example is another plot in which a trial was done in 2023, and we can clearly see, based on the analysis of 2023, that the trial was generating variability in the field. While this is a treatment effect, probably. Interestingly, if we plot the same area on the years before, we kind of detect that the position of the trial in the field was probably not the best one, because the effect that we see here, and that might have been attributed to the treatment, was already visible in the same area of the field 2 years before on 2 different crops. So this is a field that is going to be used in 2024 for a new trial, and so we have been discussing with the owner to the choice on the location of the trial. So a service that we are actually testing is to also use this information as a decision tool for trial location. So since we have data over the last 7 years, from that we can have a mean value of this metric, and also a standard deviation value of the metric. And based on the two, we can provide a relative standard deviation of the variability over time, which then is used to make, by clustering, kind of a zonation of the plots in an area that is typically highly unstable with a large standard deviation of the metric, an area that is tend to be a high GAI and stable over time, and another area where the GAI is rather low and rather stable. So the next step that we are considering for this tool is the deployment. So we now have the tool is in the form of a Python code in a Jupyter notebook that a user can run on his computer. So we are now analyzing the way and the best way to deploy and to distribute this. A second step that we would like to continue is to validate and improve the tool. And for that, we take the opportunity of this webinar to launch a call. Would you like to be one of our champion users? And other services that will come up from the discussion and the different trials. In parallel to that, we are also trying to develop. There are several activities on developing network sensors in PHENET, and these will be discussed in another webinar. But we are just mentioning here one that we developed specifically for combination with remote sensing products. If we want to take the benefits of those sensors in combination with satellites, then we need to have them in large numbers. And therefore, we are trying to develop low-cost sensors. What we have now and that are illustrated here have a canopy spectrometers, canopy temperature, air temperature and relative humidity, and also a sky spectrometers. We have 10 units under testing. We are planning to deploy more than 100 units in farmer fields. and the current setup of the stick is less than 100 euro per stick. So I'm now done with the presentation. I don't remember, Roland, if we take questions now or after. I think this is after. This was no, then I just left the missions for memory. And again, if you are interested to become one of our champion users for these kind of tools, feel free to contact us. I gave my address and not the one of Tom, who is the developer, because Tom is now working on and should prioritize on another task within the project. Thank you very much.